Okay. So I would like first to introduce you for the community.
Okay.
Yeah. So first of all, I would like to welcome all of you to our second Geological Society of Africa seminar. Our guest speaker today is Dr. Essam Heggy, and actually I would like to introduce him as an African planetary scientist. He works at University of Southern California, and he is also a co-investigator of Rosetta project at NASA. Essam obtained both his master and his PhD in astronomy and astrophysics from Sorbonne University from France. His research interests in space and planetary geophysics aim to understand water and ice distributions in Earth, Mars, Moon, icy satellite, and also near Earth objects. He is currently a member of several research teams and research projects. For example, he is member in Mars's project, the MENA, the MENA-RF. Also, he is working with the CONCERT and Wisdom Radar and other research projects. Did I pronounce the project name correctly?
Yes,
or?
yes,
Okay,
this time.
Yeah. So Essam talk today will explore a critical and I think very, very exciting question, which is, are water and life unique to Earth? Actually, I will not present the talk. I will leave it for him to present his talk by himself. So, ladies and gentlemen, please welcome Dr. Essam Heggy. Please, Dr. Essam.
So, many thanks, Tamer, for this presentation. Good morning, everybody, wherever you might be from Los Angeles. I think we have a big time difference between all of us. And so the topic of today, and I'm really very thankful for Tamer for this invitation and for the African Geological Society for this invitation. So I am an African citizen, and I did start my professional life as a assistant professor in Cairo University. And even my grant was supposed to help Africa. 22 years ago, I got a grant from the French National Center, CNRS, and engineering the grant to help developed nations to find water in North Africa. So 22 years ago, I left for France with the hope to develop methods to find water in the African Sahara. And what you're going to see today, that we were able to do this for Mars, the Moon, asteroids, comets, icy moons of Jupiter, icy moon of Saturn, and Venus, and now we are applying it for the deserts. So today the talk, it's not a distortion. It will show you how we needed to go to planets to find water underneath our feet. So I work in two places. So the first one, maybe you know very well, is the Jet Propulsion Lab, managed by the California Institute of Technology. So JPL is in Los Angeles, in the suburbs of Los Angeles. It is managed by Caltech, and it's the NASA lab in charge of most NASA advanced missions. So this is a place that most of the people in Earth science are familiar with. The first place is University of Southern California. So the University of Southern California is about 10 miles to the south of JPL, and it's actually a university who have very strong program in earth science and in aerospace engineering. It is the home of Neil Armstrong. So many of you maybe do not know when Neil Armstrong walked on the moon, he was a graduate student of the University of Southern California. So he was enrolled in the Master of Aerospace Engineering. So this is amazing, because just to take note that the first person who walked on the moon was not only an astronaut, but also was a student. So Neil Armstrong was definitely a student enrolled in the master program at that time. So we're going to be talking about a topic that is very boring, which is water stress in Africa. And I guess every time you hear about the term water stress in Africa, I mean, the first thing people hear about water in Africa in general is that they shut off the TV or they turn their back from the presentation because it's boring. And why it is boring and why water on Mars is not boring, that's what we're going to be talking about. First of all, we have to know that, just to understand why we have water stress in arid areas of Africa, basically North Africa. And this is a very simplified vision of all of that. First of all, let's agree on a few principles that water scarcity never happened by surprise. It is a result of ignoring climatic and several operational constraints. So the big problem of water in Africa is that people think that there is no problem, many. And then there is mistakes at every single level of lack of realism and comprehensive long-term vision, from science to water management, to water policies, to science policies. There is mistakes across all of these levels. There is no programs for water efficiencies in most of the nations. The whole thinking is that we should producing more and cheaper water, but water conservation is lacking behind. Water is subsidized or free in some places, so there is no market-based incentive to conserve it. And also water scientists, which are supposed to be the heroes of dry countries, are lacking resources and have a very miserable life, I would say, as employees. So they're not giving the resources even to sustain a minimal decent life. And also, we need to build a culture in our society to respect water. And we don't have that culture in our society. We think water is, we take it for granted when it is not. And we can dispute over water, but we don't collaborate to preserve water. And one of the recent examples is what we see in the Nile Basin right now. So then, a good question that may rise, why you need a guy who do research on Mars to tell you about water in Africa and finding technique to map water in Africa. So I had this nice table from an editorial which I wrote to a new journal called Euro-Mediterranean Journal of Environmental Integration. And I wanted to show people
no. You are muted, Dr. Essam.
Do you hear me?
Yes.
Yes, I think my share screen stopped. So let me put it back. Do you hear me? Hello? Oh, do you see my screen?
Yes, we see.
Yeah, okay. So this is the water budget deficit. So in Egypt, you have a water budget deficit in 2050. So this is, you have 45% of water budget deficit, Saudi Arabia 20%, UAE 34%, Oman 40%, Kuwait 83%, Qatar 60%, Yemen 190, Bahrain 108, and Mars you have zero budget deficit because nobody's using that water. And this is the research institution, the number of research institutions involved in publishing on water, at least on average one paper per year in water research from Scopus. So you see Egypt have 20 paper on groundwater per year, Saudi Arabia 5, but the place that top groundwater research is not on Earth, it is Mars. So by far, there is more water, groundwater published research on Mars than any place on Earth, even though Mars does not have a water budget deficit. And if you see the total numbers of paper published on water on Mars, it is basically very comparable. It is higher than any number of paper who is published on any water topic on any of the countries in arid areas. And it's maybe the number of institutions working on Mars research, water on Mars, outpass the total number of institutions working on groundwater in arid areas. So a little bit, so this will bring us from how we can take water research from space, which is a topic that is exciting for the community. So finding water is exciting. It's a big scientific challenge. It's a big technical challenge, but finding the same water on our deserts on Earth is a charity program. Nobody is interested. You try to publish your paper in any journal, and the editor will tell you, oh, we only publish high-level science. So why this perception that water in desert areas is not science, when water on Mars, which is a desert area, is a high level of science? And that's what we are going to talk about it here. So first of all, little introduction about water in the solar system. So first, as you guys all know, that water exists everywhere in the solar system. It is only in its liquid phase on our planet, as well as few icy moons of Jupiter. So it is on ice on the caps of Mars. It is on comets as ice. It is gas on other places, but it is always there. So then the big question that people ask all the time, especially in our home continent, Africa, why we spend so much money on finding water on these planets where we can find it on Africa. So first, each of these planets give us a preview about a phase which the Earth went through. So for instance, Venus is the past of the Earth. Mars is the future of the Earth. The icy moons of Jupiter show the Earth during the Ice Age. So each of the planets tell us something about the history of our own planet. That's why we go and explore them. And one of the big questions we have on our own planet, or the one that I'm interested in, is what is the understanding the signature of climate change in desert areas. We know very well the signature of climate change in the ice sheets, so Greenland and Antarctica. So while icy deserts or cold desert shrink in response of climate change, warm deserts, which the Sahara is one of them, and the Arabian Peninsula, they expand in response to climate change. Why? What's the mechanism? All of this, there are insights, but need to be quantified with more remote sensing observations to understand this global phenomena. So in our work, and we tried to forecast the impact of this climate change over groundwater resources. We believe that one of the strongest impact of climate change in North Africa is materialized by the depletion of groundwater resources from anthropogenic use. And so we modeled the depletion in the groundwater budget for the major aquifer system in both North Africa and the Arabian Peninsula from 2015 to 2050, based on the water budget and the data of the volume of these current aquifers and the anthropogenic discharge of these aquifers, using different climatic scenarios of the groundwater use based on the five IPCC scenarios, which called SSP 1 to 5, which is the socio-economic models and the climatic models, 5 models basically that incarcerate different scenarios of climatic changes. And we came in this, so this is basically the model. It's a very simple water budget models that took in the climate change effects and the macroeconomic data of GDP and water production, agriculture, water demand, and the renewable sources and the non-renewable sources and the conventional water resource, and basically identify the water supply and calculate the deficit between them and how it evolved from 2015 to 2050. The paper is published in Global Environmental Change, and it's in open access, and I invite you to read this paper. It's really very informative. So what we did, so this is basically where we get the numbers of the annual water deficit in billion cubic meter, so, and how it is evolving for Algeria, Egypt, Libya, Tunisia, Bahrain, Kuwait, I mean, all the countries in North Africa, basically, and the Arabian Peninsula. And what we can see for North Africa, how the water budget deficit keep rising under all the SSP scenarios. And it is basically, I mean, it's a fact that the deficit is there. And if we take under the mid scenarios, which is SSP3, the most common scenarios, this water budget will reach 40 billion cubic meter per year. So what I want you to keep in mind from this is really the summary of our results. So for instance, so this is the water budget deficit for Egypt right now in 2016. It is water deficit per capita. So right now the water budget deficit per capita is about 140 meter cube per person. And in 2050, that budget deficit will increase by the double at least. So it will reach about 260 meter cube per capita. So the Egypt and Yemen and Libya are the countries who will see increase in their budget deficit. Specifically Egypt, as you see, it's the only Egypt and Kuwait are the two countries and Bahrain, which will see a huge increase compared to what they have right now. But unlike all the other countries who have also increase in their budget deficit per capita, Egypt, Yemen, and Libya are the ones who have low GDP per capita, which will translate in increase in food prices and very little ability to mitigate that water budget deficit. So then what's the solution for these issues? First of all, let's agree that the water budget deficit in Africa, it's a problem. And it's a problem that is intrinsic to each of the countries and have to manage it. And we can't resolve a problem which we don't understand. That let's agree also on that. So the first thing is, how well do we understand our water resources? How well we understand our groundwater resources? How well we understand the climatic condition that control our water resources? And now, how much of this understanding is there in the science community as in the policymaker community? So this is an example. So most of our decision makers in Africa do not believe in climate change. And they say, oh, it's coming long enough in time that we don't need to worry about it. But unlike any decision makers, African ones tend to stay long in time to be there. So they should be believing in climate change, because most of them will actually be in power to see it. So this is an example from the Sahara, an area which is on the north of Sudan or to the south of Egypt. And this is 100 kilometer by 60 kilometer. And when you see this in optical images, you barely see evidence of water running. When you see in radar images, you see all these paleo channels about a meter too deep that radar is able to penetrate and see them. And all of them, they are witness of massive flows that existed in the Sahara from 20 million to 20,000 years ago. And that's a known fact. But just these radar images, and when I work in the radar section in JPL, it's able to develop technology to find these things deep below and tell us about basically the paleoclimatic history of the Sahara. Well, at the surface, there is no evidence of these, of course, paleochannels. So radar technique you must be all familiar with is a technique that send radar waves from 1 megahertz to 1 gigahertz, and they penetrate the subsurface, and they are able to reflect every time there is a change in the electrical properties. And it's very sensitive to soil moisture, and it's very applicable to map water resources in general and in easy words. So we did apply radar sounding. The first place where we apply radar sounding wasn't on Earth, it was on Mars. And very similar to the first place that synthetic aperture radar, which is mapping below the cloud, was applying on Venus, and from Venus was applied to Earth. So this trend is very known in Earth science, where we use planetary technique because there is less constraints of doing that on planets than is on Earth. So why all this? Why go to Mars? Mars is our sister planet, of course. It has very close characteristics to the Earth, except the Earth has its hydrosphere still preserved. Mars lost its hydrosphere. So this is just for scale dimension to show the size of the United States compared to Mars. Mars is very similar to our Sahara. It's covered with dust. So most of its hydrogeological features are really under the dust, thick dust layers. So again, this is very similar to the Sahara. So mapping below this dust and exploring what lies beneath the subsurface is very important to know about Mars hydrosphere, because the surface is more representative of the erosion more than actually the current hydrogeological processes on Mars. So this dust is very similar. As you see, it's very globally covering Mars, and very similar to the sea from the Sahara, as we see from the images of Spirit, Opportunity, and the Curiosity rover. Mars, very similar to us, has an ice cap in the north, one in the south, and both of these ice caps are believed to be the remnant of an active hydrosphere on Mars. Very similar to the Sahara, Mars also have fluvial drainage feature that are believed to be young in nature. So in sometime they are in millions years old, sometime in billion years, and we know this, and we don't see a lot of impact. So they are hypothesized to be young, and are hypothesized to occur from transient mechanism that may allow the presence of flows on Mars. So the big questions is, was Mars a blue planet? I really believe it was. I really believe Mars was an older sister of the Earth. Every single day, these evidence become very clear about oceans on Mars, about rivers on Mars, groundwater on Mars. So certainly by looking to Mars, we're looking to our past. So 3 missions I work on are dedicated to look to groundwater on the surface of Mars. Marsis, on board the Mars Express mission, was launched in 2003. SHARAD was launched in 2005 on board MRO, and ExoMars, which was supposed to be launched this year but was postponed to 2022. And 3 of them has different type of radars that look to water in the first kilometers for Marsis, and in the first few hundred meters of SHARAD, and in the first few meters for the Wisdom radar. And this whole attempt of finding water has nothing to do with drinking water on Mars, but finding groundwater on Mars is the proof that Mars and the Earth had similar past, and so they could be having similar future evolution. So, and again, I'm being very simple. I will not be technical in this presentation, but this shows the mechanism by which this radar wave penetrate. It's all function of the electrical and magnetic properties of the subsurface. And basically you have more or less transparent or slightly attenuating material layer, geologic layer, but you have a totally reflective layer of water that should generate a radar echo at the surface. So as radar see these different electrical properties, this is an example from the SHARAD data acquired over Amazonese and equatorial areas. And here we can see the surface reflection, and we can see a subsurface reflection inside of these large basins here made by impacts, and these could be the bottom of these impacts or the fill inside of the sediments of these impacts, about a couple of 100-meter deep, so less than 100-meter deep. So this is a top layer of a fill inside of these basins. So as time is going very quickly, so we use, in very simple word, the data from MARSIS and SHARAD to look to the radar reflectivity in several areas on Mars, and use several radar techniques like the time decay method to understand attenuation and reflectivity at different Mars areas. So for instance, this here is over the Athabasca area, where we try to understand these, the rafted plate, their electrical properties, to see if they originate from volcanic process or from a fluvial the process. And then we came to the hypothesis that these are more or less related to, as you can see here, to lava flows, so volcanic processes. So the observed losses are 0.18 dB per meter in this feature, which is more close to lava flows than mud flows and basically a frozen sea. The same approach, we've done it for several areas on Mars, where we look to the reflectivity to understand the compositional properties of large basins on Mars. And this is Amazonis, where very roughly we look to the radar reflectivity and we convolute the path related to textural properties to understand basically the bulk electrical properties. And here we see an area of high conductivity in Amazonis, a circular one, which could be an area where we see penetration, or could be an area where we have highly attenuated material like a buried salt lake on Mars. So many of the results we had on MARSIS and SHARAD were published in very good journals. So again, the same water on Mars made the cover page of Science magazine when we were able to map the ice caps here and show that these ice caps are layered using radar. And this layering means that they were generated over billions of years, which is mean that Mars have an active hydrosphere for billions of years, which means that Mars could have sustained the parameter necessary to develop life on Mars. Very similar paper that was published in Science by our team in Italy, where they find liquid groundwater underneath these subglacial features on Mars. And this is basically the finding of these very flat, highly reflective layer that are hypothesized to originate from waterlands underneath the ice caps on Mars. So especially the south ice cap on Mars. So all of these things goes toward evidence of life on Mars and generated and triggered all this hunt for evidence of traces of life on Mars, which are the primary targets of the rover that are all over around Mars right now. We have a large population, Spirit, Opportunity, Curiosity, and Perseverance, which is going to be landing on Mars hopefully in a couple of months. So, and all of these are looking for signature for life in a highly corrosive and erosive environment, which is the surface of Mars. So basically any evidence of this life, I really believe, would be in the subsurface and hardly findable on the surface. So these are evidence of, these are the technique for sampling that exists on Curiosity, and both future rover like ExoMars will be having also drilling capability to look for the first few meters of the subsurface of Mars with a GPR also, that I'm a member of the science team of that instrument. We also use photogeology and photogrammetry and geomorphological analysis to look to this geomorphological features very known on the walls of the craters on Mars, which are all these linear features called recurrent slope linear, RSL, which are basically, we published the paper last year with Abu Talib Saki, my postdoc, we worked together, and myself in Nature Geoscience, and we put a hypothesis that these features are not any surfacial flow and are not anything caused by any surface process, but they are produced by deep groundwater surfacing up through fractures and impact the crater. And this is, by the way, would make it one of the rare paper in Nature Geoscience written solely by 2 African scientists. And again, I mean, Abu Talib and I, we are both desert scientists. We both look for water on deserts. And amazingly, we did the same thing of looking to this feature in the Sahara, and they never ended up in a high-profile journal. You look to the same feature on Mars, and puff, you are in Nature Geoscience. And not only in Nature Geoscience, but the paper is trending and made the 2nd most read paper in Nature Geoscience. And this is where I have a problem with the science community, that still believe that finding water on Africa and geology in Africa is a charity program, while exactly the same thing on planets is a fantastic. You're going to be smart people doing this on Mars and less smarter people doing this in Africa. Not only that, but the media does the same. So our paper ended up in Fox News, CNN, New York, the Washington Post. And when we talk about finding water in Africa, hardly people just turn their back to this topic, and this needs to change. And I'll tell you how we did change it. So again, it's by the same mechanism where you see this linear feature. We see the same mechanism in areas like in Qatar, where we have this big karst feature, and we see the fracture caused by the collapse of this karst feature. They produce very similar feature to these RSL. So we also studied this in a site in Qatar that was very helpful for us to advance on these. And we published how basically water is able to move through faults and fractures from deep aquifer to the surface in the Journal of Hydrology, based on the study we made in Al-Kharara. Because we don't have so many time, I just want to show you examples of areas where we have deep groundwater underneath icy layers. And so this is the case for the Earth, Mars, and Europa, which is one of the icy moons of Jupiter, where we think there are a big ocean of saline water underneath a thick layer of 9 kilometers of ice. And you can see the evidence of that ocean in the tectonic feature you see in the ice ridges. As this ocean is fluffy, I mean the ice is being fluffy and move and make these ridges, which we see everywhere on the surface of Europa. And the JUICE mission, we did the study for the performance of the JUICE mission, which is the European Space Agency mission that will use sounding radar to probe these water lenses few kilometers deep and ones that are in the subsurface of Europa. And so we did the simulations, and basically this is detectable up to 9 kilometers deep. And this is basically a simulation of the radar reflection, how it will be able to detect these water lenses a few kilometers deep. So we can do that on Europa. We did similar exercise to go on comets and see their inner features. So this is comet 67P. It's as compared to the size of the city of Los Angeles, and I live here exactly in this part of town. And so these are very rich carbon bodies that have a lot of ice inside. And we had a radar that landed here in the upper head and was able to probe this head of the comet here. So this is just to show you example that radar can penetrate to icy environment and sandy environment. And so the Rosetta mission was by far, I believe, one of the most complicated mission in human history. If you compare it to, let's say, the Hope mission launched by Emirates, which had 3 instruments on board to explore Mars, and the Mars Express, which has about 5 instruments. Rosetta have 21 instruments and a lander. So it's really the Cadillac of space mission, and it took 10 years in space to reach its target. The solar panel are 50 meters in dimension. So it's a half of a football field. So, and this is the lander that is here. And this is when we land on the comet in 2014. And basically we landed in 8 hours, and actually the lander was lost on the surface of the comet, and we were able to retrieve it. But most importantly, my job on this mission was to use the CONSORT data to look for the inner structure of the comet and understand how much ice is in these comets, and understand how much organic material are on these comets. And as you know, there is a wide belief in the science community that water on Earth, 20% of the water on Earth is exogenic and came from impacts by comets. So this is why the importance of this mission that tell us new things about the surface roughness of the comets, and it's a very important parameter in observing them and assessing how much ice they have on their surface. And this is our images from our paper, which just published this year actually in the MNRS, which is the Royal Astronomical Society of the UK, the monthly notice of the Royal Astronomical Society of the UK. So this is also, we were able to, when the lander was lost, we were able to retrieve its position using the radar signal we get from the mission. And this was also published in Science. The first author was Roderick Kaufman, the PI. And this was, CONSORT was a major contribution, and Rosetta was a major contribution in science in telling us about how much water and ice, how much ice is in these bodies, and how much organic material is in there in these comets, and really changed completely our understanding of the evolution of comets. And this is, by the way, the lander, when we find it just the last few weeks before the mission ends. So it is here, flipped. And this was such a great mission that the Berlin Museum of Natural Science in Germany in 2017 made like a display about scientists who changed our perception of science, of astronomy and space in the universe. And you can see Galileo, Messier, Newton, and other more modern astronomers, and the Rosetta team members and myself. We were here not because we're glorious, but I think because Rosetta have profoundly changed the way we perceive comets' role in shaping the solar system. So these comets, they transport these organic material and ice across the solar system, and they can make, basically you can think of it in a very simplified way, they transport these ice so they can make maybe a place that doesn't have habitability to a place that is habitable. So bringing these volatiles and organic to it. So to all of these informations, we use them to train the next astronauts that will go to the moon to look for ice and volatiles. And I as African person, I feel humbled that I got this opportunity to work with real astronauts and the real astronaut training program in NASA, training real astronauts who've been on the space station to go back on the moon as part of the Artemis and the NASA Constellation program, who has been resurrected into Artemis. And it's a big moment to be in this front line of discovering water in the solar system. And this is the radar instrument we developed to be incarcerated on the lunar vehicle that will carry the astronauts in 2025, to be able to look to volatiles in the subsurface and try to sample these water resources on the moon, ice resources. So we did the same thing on other bodies of the solar system. So looking to ice on Vesta and Ceres on the Dawn mission. And so Vesta and Ceres are 2 protoplanets, so they are smaller than the moon, but they believe to be protoplanets, which amazingly were able to maintain ice on them. So how we did that, we used the bistatic radar experiment. We used reflection from the spacecraft, from the communication antenna of the spacecraft, to in easy word, to reflect on the surface of Vesta during occultation. And we measured that reflection on the Earth. And we made the analysis of the signal to look to surface echoes, reflections. So this is the carrier signal, and this is the main signal. And we look to the echo coming from the surface, and we analyzed the strength of these echoes and the polarization. And we made, through that, a map distribution of the surface roughness of Vesta, of asteroid Vesta, and we correlate it with the hydrogen distribution on Vesta, and we can see that every area that is smooth in blue have a lot of hydrogen. So we find smooth and hydrogen mean that there is ice in these areas. So we suggested in our paper in Nature Communication that Vesta have ground ice, could have ground ice on its surface. So somebody can ask me, so what's the point Vesta has ice or not? You see, these asteroids, when they have ice, mean that they can transport it by impact to other body, so they can generate life condition on another body. They are the carrier of life conditions in the solar system. And that's why this paper went to Nature, and it was actually selected by Nature editor when it went out, because of the importance of this, having the importance it carry for understanding life habitability in the solar system. So, and as you may know, well, none of this you may hear about it in our news, because basically, as sad as it is, the news about killing life in our continent make the first pages on newspaper, but the news about finding life, understanding life, hardly even make it to a Facebook page. So then, after all of these years, we've took all of these experiments and put it back to what my thesis was in 2002, when my thesis was to design a mission to find water in the Sahara. But the truth is, nobody was interested in finding water in the Sahara. So we have to go to Mars, Jupiter, Saturn, asteroid Vesta, asteroid Ceres, and to finally be back 20 years after to design the spacecraft that will look for subsurface, so aquifers, and understanding ice sheets in the poles of the Earth. So this is a mission totally dedicated to understanding deserts on Earth. It has been announced by NASA yesterday, actually, that this is the first phase. It's called Mission Concept Formulation. So for 2 years, we're going to be formulating this mission concept. And this is a call open to African scientists who would like to be involved in the concept formulation of this mission, which is a joint initiative between Qatar Foundation and NASA. And basically, Qatar Foundation, you need a desert entity, a desert research institute to partner for the desert research. And so why Qatar Foundation? First, because Qatar Foundation is a desert research institute, who's been there for 20 years, having the scientists from 100 places from around the world, including the Africa and the Middle East. And also because Qatar is very vulnerable, all the Eastern Arabian Peninsula is very vulnerable to sea level rise, because all that area is very flat. So understanding the aquifers and sea level rise is a primary importance of the MENA region. So the Oasis mission is supposed to launch in 2025. It's a D-class mission in the order of below $200 million. And the instrument, the radar, will be designed in JPL with partnership with the Italian Space Agency and the scientists from the area. So Oasis has the capture lead is Art Chonineski, and Art was the project manager of the Rosetta mission. So amazingly, we worked together for 10 years to find ice on comets, and now we're going to be working together to find water in the deserts. And so the mission has two objectives, and I serve as the PI of the mission. So the mission has two objectives. The first is to understand the thickness of the ice sheets and how the thickness of the ice sheets and the melting of the ice sheets contribute to sea level rise, and how that sea level rise impact coastal aquifers and impact desert areas in North Africa, and basically map the shallow aquifers in the first 20 meters of the Sahara. So the mission is not something like a story or a design. No, we have designs. We have clear design of the mission. We designed the antenna. We designed the radar. Preliminary designed all the subsystems of the spacecrafts. Has been studied for the last 10 years. So this is not a newspaper article. This is a real mission. I won't go in detail because we're not allowed to show everywhere, but I'm showing you this slide has been cleared just to understand that this is real. So the science objectives, very clear, understand the thickness and the basal layer topography of the poles of the Earth, and map the aquifer, the shallow aquifers, and understand the paleoclimatic conditions that formed them and the anthropogenic factors that lead to the depletions. I wouldn't go in detail on basically why the ice sheet dynamic is very important in understanding sea level rise, but it is. And we want to characterize all these fossil aquifers, not only because of photo drinkability, but also because they are very important in understanding environmental parameters as desertification, soil moisture, groundwater dynamic, and many things. So this is going to be a low Earth mission. It's going to be in the first 400 to 18 months, hopefully 2 years. And I'm hopeful that 2025, for once, we bring desert science from charity to science. And so there's some experiments we've done in Kuwait, and using airborne radar, and we were able to map over 6 kilometers. This is the surface reflection we got from radar sounding. And this is a preliminary result where we see the top of the water table about 50 meters deep below the surface. So we did it from airborne. Doing it from orbital is more challenging. Hopefully we'll be able to do it. We will see in 2025. And thank you, everyone. And if you have any question, I'm happy to take it. And this is my email for questions and comments, and even a proposal to join this collaboration. Thank you very much.
Wow, I have to say I am very proud of this lecture. This is a great thing. Maybe I can make an action. So actually, I have a lot of questions, but maybe I will leave the floor for others to ask. So maybe we can get questions from the audience.
Well,
I think somebody's asking, but the sound is not here.
Yeah, please, Professor.
Tamar?
Yes. Yes, please.
Tamar? Can I? Okay. Right. Bingo. I want to thank the lecturer for this. Am I audible?
Yes.
Yes.
Thank you. Right. I want to thank the lecturer for this very interesting lecture, and try to show us that, of course, we can get quite a lot of information from the space and then simulate it for our environment, especially on Earth, and particularly in arid regions where we have some scarcity of water and looking at the underground. But my question is this: how do we really model this to specific or to be relevant to the concept that we have, especially in water deprived areas of Africa? how do we also look at it from the point of view, we know most of the water accumulations are controlled by structural entities, hiatuses, fractures, faults, discontinuities. How do we simulate this data that we get from space to really be able now to ground truth it and come up with acceptable models for sustainable development of water resources, especially in Africa? Thank you.
Many thanks for your question, and that is actually a very good question, because I totally agree. If we can have as much as satellite data are publicly available nowadays, and so they are nothing if we don't have models and if we don't have ground validation. So while data is available, the funding and the skills we have in Africa to model and to ground truth are very limited, because it requires a lot to build a modeler, and it requires a lot of resources also sometimes to run these groundwater conduit models and these basically groundwater flow models. And so, and sometimes also, and again, because we address water from drinkability, so all what we care about is how we can drink water. So we tend to neglect the part on the phenomenology part, and both are correlated. I mean, we can't address drinkability and water availability if we don't know the phenomenology, and people will tend to fund the water management component, but they don't want to fund the phenomenology. If we tell people want to understand how groundwater moves through fractures in Africa, I say, oh, wait. We want tangible things that help people drink. And I am really irritated from hearing this in every single agency we went to get funding to support our research. This word of tangible. I mean, and when you look to in science policy in Africa, nothing is tangible. But when you have these minimal resources to work on water, they want quick results, and nobody want to develop theoretical models. Nobody want to develop basic understanding of this phenomenology. This is why we keep dragging behind into water sustainability, because we can't resolve a problem we don't understand and we don't model. So I share your pain, and I'm hoping a mission like Oasis, the one I just talked about, will be providing opportunity for scientists to use this data, where we're going to be mapping fractures in the subsurface and aquifers and try to correlate that in their models.
Well, thank you. Can I just ask one more question?
Yes, please. Go ahead.
The host. All right. Right. Now, thank you again so much for this. Now, how can we, as the Geological Society of Africa, I talk now as the president of the GSAF, collaborations like this, how can we practically collaborate? It would be very interesting to know that.
Very good. So the first thing, I think we should start by putting the NASA press release who went out yesterday. I think the Geological Society of Africa should put that press release, just copy paste it on the website with all the graphic it have, and we can have a comment from the Geological Society of Africa, put that Geological Society is happy to see this project. So we can put a quote from the Geological Society in it, because it will introduce it to the scientists in Africa, and then we put a call for people to collaborate. So just let's put the press release. Let's have people, my contacts are there. Let's people have who are interested to contact me. We're definitely looking to work with the scientists in the area. This is the first thing. The second thing, we in this teleconference and the Geological Society of Africa, we need to partner together to write a position paper about water research in Africa. Okay. And I will try to do my best to publish it in Nature. We publish it in Nature that enough is enough. Water in Africa is a science. It is not a charity. Stop looking at us as charity. And we need to make a clear statement for all the donating agencies that they should donate us for science, not a charity. And why I'm telling this? Have you ever give to someone $1 in the street and find him next day working with you in the university? It never happened. If they keep us in the charity place, we're gonna be always begging on their doors. And it's time this has to stop. It's time, it's long time overdue. And so this is what we need to write in the door. I think, and I think this is what we should write in the statement paper. So these are the two actions I'm suggesting to be carried in the next month. One to be carried today, actually, to post the press release, and one to be done in the next month. I'm gonna write the statement paper, and then we're gonna circulate it among us, and then we propose it to nature.
Thank you very much. This has been very interesting. Sorry, Tama, I don't want to dominate the discussion. I just want to give you an instruction that you follow these up immediately and get these 2 action points sorted out immediately. So you have the authority to do them and get it
we'll do it.
done.
Yeah. So actually, I am also editing the website of the Geological Society of Africa. So I think by this weekend you will find the news there.
Very good. Very good.
I have actually a question.
Okay, I have to go in 5 minutes, but so we have 5 minutes for questions.
Okay, just one question for me. Maybe I open it for other. If anyone else has a question, please, Yusuf. The sound, no, we can't hear you.
And now maybe it's okay?
Yes.
It's okay, yeah. My question is maybe without any connection with your talk, but as geologist and as petrologist, one of our concern is the origin of water on Earth. That is a geochemical issue. Is it any connection between your work and this issue, please?
So there is a lab in France, it's called CPRG, who published the paper about finding evidence of water in meteorites. And they did that for the last 20 years. And I think it's in Nancy in France. And for the last 20 years, they've been advocating that meteorites have signatures of liquid water, and that liquid water have been coming, 20% of it from meteoritic and impacts event. So yes, I agree, it's a geochemical issue. And from comets, we see that comets have a lot of ice. So if they impact our planet, they should be bringing substantial amount of volatiles. So it is an open question in the science community.
Thanks so much, Prof.
Other question from the audience? Yeah, please. Mariam?
Well, thank you. Thank you for the lecture. And I just have a small question. Apart from what you have given for us, I mean, as radar images and images, what kind of data do we need to just think of that model you were talking about, and how Qatar will be of use? Yeah, you just told us how you explained that it is a desert, and also it is flat, so you can hold on the study, the practical study. But what kind of data do you need to collect apart from the images in order to put on together the model?
Okay, that's a very good question. So in 2025, when this data will be available, it's going to be a bunch of subsurface radargrams that shows different reflectors on different areas. And then calibrating this data with well logs in some spots will be vital to calibrate the depth of a scene from radar. So I think we will be still needing some well logs data to calibrate the radar data in 2025. So what place like Qatar will bring? It's definitely you can't formulate a mission for water science without water scientists. So it's the platform. Qatar Foundation will be the platform by which the scientists from desert areas, including of course Africa, will meet and will be able to have a place to talk and put the mission requirement. What I mean by mission requirement is what's the resolution we need to image, horizontal, vertical, what's the data sufficiency, what's the data coverage. All of that you need a Desert Research Institute to host this discussion, and we get the recommendations to implement in the mission. And you can't do that without a local partner in the area. And we called for across 10 years for local partnership, and we looked to Sultan Qaboos University, to Kuwait, to NARS in Egypt in 2010. And so it's after many discussions and many, this is the opportunity, the funding program that was available to support a part of the mission was made actually Kuwait Institute for Scientific Research and Qatar Foundation.
Okay. So thank you very much, Sam, for this very interesting talk. I don't think you have time for my questions, but at least I have your email, so we be in contact, and I will send you my questions, which is related to the data and the publishing of the data itself, especially from the polar region.
Okay.
Yes. Also, I will put on our website today or tomorrow the announcement about this project, the Oasis project, and then we'll be in contact to push
to write the paper.
Exactly, to write the paper, and also to get information and ideas from you how to push our political people in Africa to finance and help scientists to push this forward.
The scientists need to step in to the water issues in Africa. We can't leave water issues to be a political issues where people are fighting and become a nationalist or national security. It has only become a national security when it has been ignored. But it is a science question that can be achieved by negotiation and with the scientists.
Super.
Okay.
Thank you very much, Essam.
Okay,
and,
many thanks, everyone.
I would like to thank all of you, and I would like to close the session. So, thank you.
Okay. Thank you. Bye.
Thank you. Thank you very much. Very interesting lecture. Thank you.